Good day, grade 12 learners. Welcome to today's physical science lesson. My name is Mashidu Mamburu. This lesson is brought to you by the Gauteng Department of Education in collaboration with the Saipono Discovery Center. Thank you very much. We are still cruising nicely with paper 2. We are focusing on electrochemistry, which is your galvanic cell and your electrolytic cell. So what we're going to do, we're going to consolidate or complete the galvanic cell, and then we do the electrolytic cell. I hope you will enjoy this part of paper 2. There are a lot of marks here, question 8, question 9. We are saying be able to collect these marks. We're going to give you skills and strategies on how to do well as far as this two questions are concerned. Now, with no wasting of time, I've indicated this is paper 2. It's paper 2, which is still 150, and we have said it's 3 hours. So I know you know the structure of the paper, and we are saying here we are dealing with electrochemical cell, which is your galvanic cell, and your electrolytic cell. So that is our focus for the day. Now, with no wasting of time, we talk to the periodic table. Remember, as far as paper 2 is concerned, it is all about periodic table. This is your friend. This is your friend. You keep it closer to you so that you are able to enjoy. So I'd like to remind you that everything in the periodic table we have indicated on the left of the periodic table, we are having metals here. We have metals, your group 1 metals, your group 2 metals, your transition metals there. You are having group 13 metals there, and then you are having your semi-metals, which is in yellow there. Then we have non-metals there, and your noble gas, which is your group 18 elements. So always remember that. Hence, all the reactions, they take place in order to behave like group 18 elements. So everyone else wants to be like group 18 elements because they are stable, they are fully filled. So we have reactions so that everyone becomes fully filled. All these atoms, they will want to be fully filled, and they do that by either losing electrons or gaining electrons. So the only reason why substances will lose electrons or gain electrons is because they want to attain group 18 status. They want to behave like noble gases, where they are fully filled and they become more stable. It means they are not stable where they are. They are more stable if they are in group 18. You will have realized that group 18 are very much unreactive because they are fully filled. So all of them want to do that. We've indicated the group 1 elements will are most likely to lose one electron. Group 2 most likely to lose 2 electrons. Group 13, where we have aluminium, likely to lose 3 electrons. I've indicated as well, want to emphasize that the metals are most likely to lose electrons under spontaneous reaction. Now, the non-metals are most likely to gain electrons, and we've indicated that when substances lose these electrons, they become positively charged, and we call them cation ions. And then, so when substances gain electrons, they become negatively charged, and we call them anions. So it's very much important to have that understanding as we start with our lesson. The most important part being these definitions, we always emphasizing definitions from the exam guideline so that you are able to define all of them. Now I will be quick when I deal with them because I want us more to focus on problem solving today, not necessarily on the theory part of things. In grade 11, you have done your oxidation, which we said is loss of electron or increase in oxidation number. Remember, you can define oxidation in terms of electron transfer or in terms of oxidation number. And reduction was saying is a decrease in oxidation number or gaining of electrons. So saying gaining of electrons is reduction. Don't forget this mnemonic that we are always giving you to remember how to define. Remember, we said this loss of electron is oxidation, and that happens by the reducing agent. What is a reducing agent? We said it's a substance that undergoes oxidation, and that substance we said is oxidized. So don't forget that. It always reminds you how to define this. And we are saying gaining of electrons is reduction, and that's where you get your oxidizing agent. So in oxidizing agent, we're saying it's a substance that undergoes reduction, because we want you to get total on the definitions, and you know that the oxidizing agent must be reduced. And then you know the anode, we said is an ox, which you said is an electrode where oxidation takes place, and the cathode is an electrode where reduction takes place, we say red cat. So don't forget this, because they're able to make you to remember this definition. I've defined for you oxidizing agent and reducing agent as well. So you're able to do that. You have done in grade 11 the oxidation numbers. They are very much important, because if you understand oxidation numbers, you will be able to identify oxidation and reduction reactions, as well as electrolysis, which is what we're going to do today. Your mind map to indicate under galvanic cell, to say this is our focus, and we are going to do questions based on the galvanic cell. Oxidation numbers, so that you are able to remind yourself that those general rules, to say we deal with substances, which is your compounds, your ion, and your elements. Remember, we said when you have elements alone, they have now oxidation number of 0. But when you have a neutral compound must add, the oxidation numbers must add up to 0. For example, we showed you with carbon dioxide there, where you had oxygen, which is -2. For CO2, we said oxygen is -2. -2 times 2 gives you -4, and that will be +4. Then it must lead to 0. Hence, we are saying always a neutral compound, when you add the oxidation numbers, must give you 0. And we are saying in an ion, for example, a sulfate ion there, the oxidation numbers must add up to the charge on the ion, meaning that on SO4 2 minus, the answer must be -2. So if we know oxygen is -2, -2 times 4, that will be -8. Then meaning that it will be -2 plus 6 plus 8, that gives you +6. So you know that for sulfur the oxidation number is 6, for oxygen is -2. So you're able to identify that all the time. And we are saying free elements have oxidation number of 0. Group 1 elements, most likely they will form 1 positive charge, cation, and then +2 for group 2 elements. Group 13, where we have aluminium, we have oxidation number of 3. And the hydrogen is a +1, and then and we have exceptions there when it's with boron, and is able to be -1, a hydrogen there. That is the exception. And for oxygen, we're saying it's almost always -2, the oxidation number. This is just to remind you, so that when you're dealing with this section, you're able to always remember. Remember the non-metals, we said they are most likely to gain electrons. Group 17 elements will gain 1 electron. Group 16 will gain 2. Group 15 will gain 3. Remember, when you gain electrons, you become an ion negatively charged, meaning that you have excess of electrons. But when you see a positive charge, it shows that we have a shortage of electrons. Now, in the galvanic cell, we've indicated that this is a cell that converts chemical energy to electrical energy. So always remind yourself of those energy convention, to say when I define a galvanic cell, I will know that it's chemical energy to electrical energy. I always want to emphasize that don't say it's a mechanical energy. Remember, mechanical energy is for paper 1 when you're dealing with generators. Here in paper 2, we're talking about chemical energy to electrical energy. And we're saying this cell is a spontaneous cell and is exothermic, which means energy is released. Remember, exothermic, we're saying energy is released. And endothermic, we're saying energy is absorbed. So in this case, energy is released. Hence, we are releasing electrical energy from chemical energy to electrical energy. So don't forget, those are 3 most important things. That this is spontaneous reaction. We don't need any other energy source so that the reaction takes place. In this one, it takes place spontaneously and is exothermic. And the apparatus, you will see, we will have 2 different metals, each immersed in separate beakers. This is not a general rule. Remember, sometimes we have what is called a direct electron transfer, where that can happen in one beaker. So it's important that you have that in your mind. You don't just claim that always it must be 2 beakers, but we are saying there is direct electron transfer as well. But hence, a normal galvanic cell will look like that, where you have 2 beakers, and then the 2 beakers, then we are saying that, for example, this is zinc copper cell. It's a normal cell that we like to always explain it, because when you understand it, you'll be able to understand other cells. Hence, we ensure that you understand that one. And then the most important thing is that the anode is a negative electrode. So a negative electrode, even when you look at the standard electrode potential on table 4A and table 4B, that negative one for question 8, we are saying now that is your anode. That is the one that undergoes oxidation. Remember, the anode is where oxidation takes place. And the cathode, copper, we are having copper there, that is a positive one. It gains the electrons, and then it undergoes reduction when it gains electrons, because electrons are negatively charged. Now, it's important to know that we have the oxidation half reaction, which is the loss of electrons. We have the reduction half reaction, which is the gaining of electrons. Now, as well, you know that we have our electrolyte there, which is our, if we have a zinc, it must be inside a zinc solution. You can't have zinc and the solution is copper. No. If you have zinc, the solution must be having zinc ions as well. If you are having copper, the solution must have copper ions. So it's very much important that you understand that if I have an electrode, that is a metal, that metal ions must be in the solution. It's important, and we are able now to talk to the issue of the oxidation half reaction reduction. We add the two, we're able to get the overall cell reaction. Remember, you write what is on the left of the half reactions, you write it on the left. What is on the right, you write on the right of this one. Hence, you'll have zinc and copper 2 plus on the left. And remember, the reaction is always between strong reducing agent and strong oxidizing agent. So what we're saying zinc is a stronger reducing agent. Copper 2 plus is a stronger oxidizing agent. They always is a stronger reducing agent and a stronger reducing agent reacting together to form a weaker oxidizing agent and a weaker reducing agent. So on the right of the overall reaction, we have the weaker agents. On the left, we have the stronger agents, which is your reducing agent and your oxidizing agent. So you are able to remember that, and then we are able to move forward with no problem. But now, as I indicated, our focus today will be mostly on doing question, and mostly on electrolytic cell. Hence, you'll see that I'm moving. I want us to be able to cover as much as we can so that you are able to enjoy the session and you are able to prepare yourself now for your exams. Now, we are saying, let's look at a multiple choice question, which says, which one of the following statements regarding the anode? So it's important that whatever we're going to talk about, it applies to the anode. Remember, in this case for galvanic cell, we said an anode is a negative electrode. A negative electrode of a standard galvanic cell. So galvanic cell, we said this one converts chemical energy to electrical energy. We said this one is spontaneous. We said this galvanic cell is spontaneous. And we said it's exothermic because energy is released. We convert chemical energy to electrical energy. So that is our galvanic cell. Now let's look at the options that are given. Now I want to ensure that we move together here. The importance during revision of multiple choice is not only to identify the correct answer, is to understand why other answers are wrong, because you learn from that process. Now, what am I saying? I'm saying our main focus here is not to identify what is wrong. It's not to identify what is right. It is to say, if you are saying A is not right, respond to say which one, what was supposed to be, what was it supposed to say. For example, let's look at A then. It's saying the anode accept electrons. The anode, remember we said an ox. We said an ox. At the anode, there is oxidation, which is loss of electron, which is oxidation. So the anode does not accept. At the anode, we lose electrons. We don't gain electrons. We don't accept electrons. But now, if you were to put a cathode there, will that statement be correct to say at the cathode accept electrons? No, it's not necessarily a correct statement that a cathode accept electrons. So the correct statement is that at the cathode, that is, a cathode is an electrode. It's an electrode where reduction takes place. You see, not that itself the cathode, because you will find that your cathode is copper, for example. In the zinc copper cell, for example, your cathode is copper. So copper does not accept electrons, but electrons are gained by the copper ions. You see, now it's important. So when you say a cathode accept electrons, that is wrong, because you are saying copper. If copper is that cathode, copper accept electrons. It does not. It's the copper ions. So it's the ions of that electrode that are going to accept those electrons. So it's important that we remove the misconception you are able to move with us. You understand where we're coming from and where we're going. Now let's look at number B. The mass of the anode decreases. Remember what we said. We said an anode is an electrode where oxidation and where oxidation takes place. So oxidation is loss of electrons. So if for example your anode is zinc, so if zinc is losing electrons to form zinc 2 plus 2 electrons, definitely zinc will decrease in mass. Hence statement number B will be correct, that the mass of the anode decreases. Now, the concentration of the electrolyte in the half cell containing the anode initially decreases. You will see that as zinc loses electrons, it forms zinc 2 plus, which means that the solution, the electrolyte solution, is increasing. It's not decreasing. That's why that statement is wrong. You see, at least you are revising now. You are seeing why this answer is not correct, and then you are able now to have even much depth in terms of your understanding. The anode is the positive terminal of the cell. Remember, for galvanic cell, we are saying the anode is a negative electrode, not a positive, but a negative electrode. That's what makes that answer wrong. So when you are choosing B, in your revision, you have learned about the others, because even if you don't know what will be the correct answer, you're able now to ask yourself and ask your teacher and research for yourself to know what is happening, because this is your teaching tool. You are teaching yourself, you are learning now, because teaching has happened. Now it's time for learning. When you are revising, there is a lot of learning, and then you can only learn if you are solving problems. Now, consider the reaction represented by the following equation. We're given 2Ag plus, I'm writing it because I want you to see the superscripts there, which is aqueous solution plus copper, and then you are forming Ag and copper 2 plus. So you can see I've already indicated to yourself that in our reaction, on the reactant side, we have a stronger oxidizing agent and a stronger reducing agent. Remember, the metals, when they are not charged, they are reducing agents. So you will see that this Ag plus is your oxidizing agent, stronger oxidizing agent, and copper is your reducing agent. And I want to emphasize this, that the agents, the stronger agents, are always on the left of your overall cell or net cell reaction. So it means this is a stronger oxidizing agent, this is a stronger reducing agent. They always react to form the weaker ones. So you are able now to know that whatever the agent that this will be a weaker reducing agent, and this will be a weaker oxidizing agent. So stronger oxidizing agent react with the stronger reducing agent to form weaker reducing agent and weaker oxidizing agent. So you're able to see that. So when you see the pluses, you know those positive the ions, they're able to show you that these are the two oxidizing agents. They are positively charged there. Then you're able to see one of those two it must be stronger. The stronger is on the left of the reaction. Hence we are saying Ag plus is your oxidizing agent in this reaction, because it's stronger than the copper 2 plus, and the stronger the agents are on the left of the reaction. So you are able to identify it like that. Now let's look at this one, which is in the electrochemical cell below. The letters X and Y represent two metal electrodes. So we have two metal electrodes. When the cell is functioning, that is X and Y, they are saying when the cell is functioning, the electrode X gains mass. So that is very much important. Hence, it's written in capital letters. But what are we saying? We are saying as time goes on, we won't be writing electrode X gain mass in capital letter, because we make it obvious for you to remember. We'll just write it with the same letters as others. So it's important that you just have understanding. You don't want us to give you the clues to say what happens. Now, when X gains mass, you know the anode, we said an ox and we said red cat. So you are able to remember that at the anode is oxidation, which is loss of electron, which is oxidation. So you know that the anode must decrease in mass, and the cathode must increase in mass. In mass. So you're able to see reduction is taking place at the cathode, then it decreases. It's not losing, it's gaining electrons, the ions in that side. So you're able to see that, okay, X gains mass. It means X is cathode because it's increasing in mass. So when it increases in mass, it's a cathode. And when you write your cell notation, this is what we refer to as cell notation. We're saying you always say A, B, C. A for the anode, and then B for the salt bridge, and C for the cathode. Another one we say all clever. All the learners are clever. So if I say all clever, then you are able to see that, oh, all my learners are clever. We start with the anode, salt bridge, then cathode, so that you don't forget that. You are always remembering that, okay, according to these statements, X gains mass, it makes it a cathode. So if X is a cathode, the cathode must be on the right of the salt bridge. So we're looking for situation answers that have a cathode, that have X on the right of the salt bridge. Now, our cathode is always on the right of the salt bridge. I'm emphasizing that so that when you get questions, you're able to respond to them. Now, let's look at this. When it comes to this first example, number A, the option number A, you are having X plus, which is aqueous, forming X. Now, what you must understand is that always when you are writing the cell notation, here at the beginning and the end, there must be solids. That is the first thing you understand. So if you have an aqueous solution, for example, here you have aqueous solution, you can't have an electrode that is a solution. An electrode must be solid. So it fails that our conductor cannot be aqueous solution. Our conductor must be solid. So obviously you will say my answer must have solid, and the ion that is gaining electrons must be next to the salt bridge. So this is the correct answer. You are able to choose number A, and you know why D is wrong. D is wrong because outside we cannot have aqueous solution. The aqueous solutions, they must be next to the salt bridge, but outside always we must have a solid because those are our conductors that are conducting our electricity. So I hope you got that. You're able to see why this one will be wrong, and you see why this one will be wrong. This one will be wrong because what is gaining mass, what is the cathode, is X, is not Y. So this is wrong. This is wrong because aqueous solution is outside. This is wrong. Aqueous solution there, aqueous solution there. So you see that your answer was almost obvious that it must be A, the correct answer. Now let's look at activity 2 then. Now, what we want to emphasize here is that some of the questions you will be given the cells, some of the questions you will be given the cell notation, like this one. Look at that question. We're given a cell notation, and then it is still that cell. The main thing that you have to understand is that when I have a cell notation, I'm having the anode. We said all clever learners. So all clever learners. So you know that we have the anode, which is your zinc forming zinc 2 plus. We have your cathode, which is your Ag plus forming Ag. So outside here, we have solids here. Always, I told you, I emphasize that always outside we have solids because these are our conductors, which is our electrodes. Now, this line we indicated, I want to emphasize that it shows that Ag plus and Ag are in different phase. So the other one is aqueous, the other one is solid. So as long as the phases are not the same, you will write a solid line there between them. So that line is important because it's showing that they have different phases. If the phase is the same, it will be a comma. But in this case, we make solid lines because it's showing that those are like that. So you're able to see that, okay, for the anode is zinc forming zinc 2 plus. So you can see already that you are able to answer your question to say, okay, the anode is zinc forming zinc 2 plus, which means it's losing 2 electrons. And then for the cathode is Ag plus, gaining an electron to form Ag. You can see we end up with Ag. Now here we start with zinc, we end up with zinc 2 plus. This side we start with Ag plus and then we end with Ag. So you're able to read it from there, and you are able to answer your questions and enjoy the section. And with no wasting of time, you are able now to write the overall or net cell reaction. Remember, for you to balance this, you have to first balance the electrons. You can see that for the zinc, we have 2 electrons, hence the charge is +2. +2 is showing that we have lost 2 electrons. But Ag plus is showing you that Ag plus, it means that it's running short of 1 electron, meaning that for it to become Ag, it must gain that electron. Hence, we're able to write the half fractions like that. And then you must first balance the electrons before you write the overall or net cell reaction, which means you're going to multiply this by 2. You multiply that by 2, so that the electrons are 2, 2. When the electrons are balanced, I said to you always, what is on the left, you write on the left. We have zinc plus 2Ag plus, which was said here, zinc will be our stronger reducing agent. 2Ag plus will be our stronger oxidizing agent, because the agents are always on the left of the overall cell reaction. And then you cancel the electrons, and then you write your zinc 2 plus 2Ag. You see, that is your overall balance, overall cell reaction. So you are able to do all that, and you are able to get to answer all your questions. Now look at the questions there. 2.1. It was write down the anode and the cathode have reactions, which is what I've done. On the anode is zinc becoming zinc 2 plus, which means it's losing 2 electrons. You can copy it from the table, or you can just look at it that way. You're able to get 2 marks for writing that. Write down at the cathode, the reaction that takes place at the cathode is 2Ag plus an electron, is Ag plus an electron forming Ag. You do that. Write down the overall. You are able to first balance. Remember to write the overall. Always let's balance the electrons. Then you're getting 3 marks for doing that. And look at how many marks you are getting. Look at the last question there, saying, what is the direction of the electron flow? So you know that electrons, they flow from zinc half cell to the copper half cell. So they flow from zinc half cell to the copper half cell. So you are able now to collect your marks. We are saying question 8, these are your marks. Just collect them and enjoy yourself as you do this section now. To do a much longer question, then as we wrap up galvanic, so that we are able to do electrolytic cell. Now, the figure, I still gave you zinc copper to say in the zinc half cell, the following reaction takes place. You have zinc losing electrons to form zinc 2 plus 2 electrons. You have a copper 2 plus gaining electrons. In which electrode does oxidation occur? So you're able to check the electrode is the zinc one, which is the anode. Remember, the anode is the one that loses electrons. So we said loss of electron is oxidation, reducing agent is oxidized. So you're able to remember that this is gaining of electrons, which we call reduction, which is our oxidizing agent, which is reduced. So you're able to see that okay, in which electrode does oxidation occur? It's in the zinc half cell, and give a reason for that, because the zinc is an anode. How do you know that zinc is an anode? Because it has a lower standard reduction potential, so it loses the electrons. In which electrode does the reduction occur? And then reduction occurs at the cathode. It takes place. Which one is our cathode? Is the copper 2 plus. Copper 2 plus is the one that is gaining electrons. You can see that copper 2 plus showing you can't gain zinc cannot gain electrons, but copper 2 plus, because it's running short of electrons, is the one that gains electrons. So you are able to respond to this question. What happened to the mass of the zinc? Remember, zinc we said is the anode. The anode will decrease in mass. What will happen to the mass of the cathode of the copper? In this case, copper will increase in mass. Don't forget, when the mass of the anode decrease, its solution, which is the zinc 2 plus solution, the electrolyte, increases. As the mass of copper increases, the copper 2 plus electrolyte solution decreases. So you must know what increases and what decreases, because it helps you as you answer question. What is the function of the salt bridge? Remember, we're saying the salt bridge has 2 functions, which is to complete the circuit. It means without a salt bridge, the circuit is incomplete. And to maintain neutrality, to maintain electrical neutrality. So it maintains electrical neutrality. So that's what it's doing. It completes the circuit. And it maintains electrical neutrality by allowing the movement of ions. Now, the ions here in the salt, you'll find that your salt, maybe, so in this case, it can be your, say it was potassium nitrate, for example. Then if that is your salt, you know it has a cation, K plus, and NO3 minus. So we're saying the cation will go towards the cathode, which is this side. The cation will go towards the cathode, and the anion to the anode. So don't forget that to say, we are saying, don't forget, anions, they go to the anode, the cations, they go to the cathode. What is the function? Is to maintain electrical neutrality. So I hope that will help you as you answer questions and you are able to move. Will the electrons move from zinc to copper or from copper to zinc? You know that they always move from zinc to the copper, I've said, because zinc, they always move from anode to cathode. Use the scientific notation, the cell notation, to represent this galvanic cell. Remember, in this galvanic cell, we said zinc is going to lose electrons to form zinc 2 plus, and copper 2 plus is going to gain electrons and form copper. So you are able to see that, okay, in the anode, remember, we're saying all clever learners. So you are all clever, and then, or you are saying A, B, C, the B for the salt bridge. So you are able to say, okay, anode is zinc becoming zinc 2 plus. I have explained that this line shows you that the two are in different phases. The other one is aqueous, the other one is solid. And then you can write the solution to say this is 1 mole per cubic decimeter. And then you write the salt bridge. After salt bridge, you show that copper 2 plus here, this side, you will write copper 2 plus forming copper. And then you can indicate the concentration of copper 2 plus, which is initial concentration is 1 mole per cubic decimeter. So you are able to get that, and you are able to answer the question, and you are getting your 3 marks for doing that. So I hope this helps you, and you will practice as many question papers as possible. Now, as we move, I want us to look at this table. Remember, we have table 4A and table 4B. Those two tables are, I would like to say, they are the same tables. They are the same. The difference is the entries. If we look at the table 4B, I just snipped these compounds or molecular substances because they are the ones that we are going to do a question with, the next question that we are going to do. But if you look at table 4A, it will start with positives and end up with negatives. So it's just reversed in another way. So this one, table 4B, starts with negatives going towards positive as we move down. So you can see, remember what we said. We said on the left here, we're having oxidizing agents, and on the right, we're having reducing agents. And as we go up, the more negative you become, you are a stronger reducing agent. But as we go down, we find a stronger oxidizing agent. Remember, if going down is a strong oxidizing agent, it means the ones remaining are weaker, which will make magnesium 2 plus, for example, a weaker oxidizing agent. But this makes magnesium to be a stronger reducing agent. So I want you to have these tables in your mind because they will help you to respond to questions as well. Now, the question that we're going to do will refer to the table and use it to answer some of the questions. Now, let's look at this one. It says activity 3. The electrochemical cell illustrated below is set up under standard conditions. It's very much important that you remember what are the 3 standard conditions for these galvanic cells that we are doing here. Remember, we're saying the initial concentration must be equal to 1 mole per cubic decimeter. And we are saying that the temperature must be 25 degrees Celsius. And we are saying the pressure must be 180 m, or if you don't want to use atmospheric pressure, you can say pressure must be equals to 101.3 kilopascals. So you got to know that those are standard conditions. It means this reaction happens under standard condition. That's why when you are calculating EMF, we are saying EMF of a cell is given by E cathode. I'll just take the first formula there, which is E cathode minus E anode. So you are able to know that this is now the formula that we use, that 0 that you see there at the top is showing you that that is under standard conditions. It means for this one, concentration applies, we have gases, concentration, temperature applies, and pressure applies. On this one, all of them apply. But on the zinc copper one, for example, you will have seen we don't have any gas. If we don't have a gas, pressure does not apply. Remember, we said pressure affects only gases. When you're doing chemical equilibrium, we said pressure affects only gases. So here, pressure affects because we have a gas. You can see we have hydrogen gas there. Those bubbles, they're able to show you that a gas is there and is going to be formed there. Now, let's look at the question. It says component X completes the circuit in the cell. State one other function. You see, our salt bridge now is component X. So what are the functions of the salt bridge? We said is to complete the circuit and to maintain electrical neutrality. We said it allows the movement of ions. I've shown you that the cation will go to the cathode and the anion will go to the anode. Define the term anode. Remember, we said an oct. Don't forget, we said an oct. But if you are forgetting, if you go to your data sheet, you will find those three formulas. You will have E of a cell equals to that, or E reduction minus E oxidation. So you're able to see that, anode is an electrode where oxidation occurs or take place. It's an electrode where oxidation occurs. Hence, we are saying an ox, so that we are emphasizing that so that you don't forget that it is at the anode where oxidation takes place. Now, identify the anode in the cell above. Remember, we said the electrodes must be solid, and it's very much important for you to understand that our anode here is magnesium. How is that so? Say, how do you know that magnesium is our anode? Remember, I showed you the table where we had magnesium on table 4b or table 4a. You go there, you will find magnesium written like that with a standard reduction potential of negative 2,36, and we had hydrogen, the hydrogen one, 2 hydrogen plus 2 electrons forming hydrogen gas. So you're able to see that this one is 0,00. So you're able to know that your anode is a negative electrode. So you're able to see that this is my anode, and the positive one, which is your 0 there, is your cathode. So you're able to identify there that you have the anode and the cathode. And if you are looking at table 4b, it's arranged in such a way that the negatives are at the top of the table and the positive at the bottom. So you're able to see that the anode first, then the cathode on that table for this galvanic cell. So that makes magnesium our anode. Remember, we said that the electrode must be solid. So I'm emphasizing that so that we are able to move together. Now, write down the reduction half reaction. So for the reduction half reaction, if you go to the table, for example, we are talking here about this reaction and this reaction. That's what we are given there. And we are saying the anode, it must be reversed, and the cathode must continue like that. So if we are saying write down reduction of reaction, we are still simply saying this one must be able to be 2H plus 2 electrons with 1 arrow. Then it forms H2 gas there. So we're having 2H plus 2 electrons forming H2 gas. So you are able now to get your 2 marks for writing the reduction half reaction. That negative one, which you said is a stronger reducing agent. Stronger reducing agent will definitely lose electrons because electrons are negative, and you expect electrons being lost from negative. Maybe another way of explaining it to you so that you have an understanding. We are saying now that if I was to do what is called, remember what we call a number line, we'll have 0 there, we'll have negative 2 somewhere there, 2,36 somewhere there, we'll have 0 there, we'll have the numbers maybe positive 2, 36 somewhere there. So what I'm saying is that if you do a number line, electrons will always lose them going towards like that. It is the negative one that loses electron. So this negative one, this one, anode, our anode now, a negative electrode, will lose electrons towards that. This one that is positive, it will gain electrons, which is now these hydrogen ions. So you see that between these two, it is the negative that will lose electrons. It is the positive that will accept those electrons. So you are able to have that understanding, and I hope it helps you. Name or formula of the reducing agent, already indicated that your reducing agent are on the right, oxidizing agent on the left. And we said as we go down, we are finding stronger oxidizing agent. As we go up, you see the arrows there is for reducing agent. So magnesium is a stronger reducing agent. Now you are able to know that that is magnesium. They said name or formula, so you can say Mg for the formula, or you can write magnesium in full. Now they say calculate the initial EMF reading of this cell under standard condition. Hence I've indicated that as you write the formula for EMF, E of a cell, you know that zero there with lines with that writing inside there. It stands for standard condition. So E of a cell is equals to E cathode minus E anode, meaning that if you write this formula without writing this theta like or zero there, you are not going to get it correct. So you copy the formula from the data sheet as it appears in the data sheet so that we don't have problem. Now E of a cell, we said our cathode was hydrogen, which was 0, 0. And magnesium, you said is negative 2,36. I hope you will remember that. And negative multiplied by negative gives you a positive, which is positive 2,36 volts. Remember, then, as we said, this is a spontaneous reaction, meaning that we are agreeing, me and you, that your answer must be a positive answer as you calculate EMF of this cell. So in the event you are getting negative, you must be able to ask yourself a question: have I made a mistake and put a cathode where I was supposed to put the anode and all that, so that you are able to get the correct answer. I hope you understand me in terms of that. Our last question, it says the magnesium Mg2 plus half cell is now replaced by copper 2 plus. We like doing this these days where one is being replaced by the other. Remember on our table we were having magnesium 2 plus, let me write bottom here, magnesium 2 plus 2 electrons forming magnesium, and we were having 2H plus 2 electrons forming H2, and now we are having copper 2 plus 2 electrons forming copper. I want you to look at this three. Look, this one we said is negative 2,36. This one we said is 0,00. Now we are adding copper, that is positive 0,34. Now you can see now we're going to switch, because now which one is more negative? Is 0. 0 becomes more negative because we no longer have this. This has been removed, replaced by this one. So meaning that now the hydrogen one becomes the anode, and the copper 2 plus 1, it is the cathode now. See, because of those values, because we're saying that which is smaller must be our anode, must lose electrons, but that is positive will gain electrons. So you are able to do that, then meaning that if you do the Z method, you just write Z there, the first one must reverse. It must reverse, hence that H2 now is going to form 2H plus 2 electrons, and the copper 2 plus will now be the one that is gaining electrons. So let's hear the question. I was just explaining so that you have understanding of when we replace, what does it mean? It means we no longer have the Mg2 plus, we now have the copper 2 plus. So now we are saying it is found that the direction of the electron flow changes, and we agree that now is H2 now that is going to lose electrons instead. Fully explain why there is a change in the direction of electron flow by referring to the relative strength of the reducing agents. This is very much important. Remember what we said. We said on the right here we have reducing agents. On the left we have oxidizing agents. So the question says leave oxidizing agents alone. Talk about reducing agent. So you will know that as we go up, if you look at the arrow of your table, as you go up there, where the arrow is pointing, it means that you will say now, oh, okay, H2 is a stronger reducing agent, or you will say copper is a weaker reducing agent than H2, or H2 is a stronger reducing agent than copper. You see there now. Therefore, H2 will be oxidized to H plus, or copper 2 plus will be reduced to copper. So you're able to get your 3 marks like that. So you're explaining that because this one, H2 is stronger, it must win. So H2 is a stronger reducing agent. Therefore, H2 will do what now? H2 will lose electrons, or will be oxidized to H plus. So that's what you will do it. Then you are able to get your 3 marks in terms of your explanation. Now, we are moving now to electrolytic cell, and then we are saying here under electrolytic cell, we are dealing with only 4 processes. So we don't do aluminium. I want to emphasize that to you, that we are doing 4 processes. Is decomposition of copper chloride solution. Copper chloride, when we decompose copper chloride, we simply want to form copper and Cl2. So we just want 2 reactions that will form copper and Cl2. And then remember, the copper in copper chloride is a copper 2. So you know that the copper that we're talking about is a copper 2. And then remember, if you put copper chloride in water, it will ionize and form copper 2 plus and 2Cl minus. So meaning we want 2Cl minus to form chlorine, and we want copper 2 plus to form copper. That's simple and straightforward. Now, the next process that we do is electrolysis of concentrated sodium chloride solution. Concentrated sodium chloride solution, that is sodium chloride. In this case, our sodium chloride is like that. But during the process, you will see that we're going to form Cl2, chlorine gas, and we won't form sodium in this case. Remember, is solution. So it's an aqueous solution, which means it's sodium chloride in water. Instead of sodium plus gaining the electrons are going to be gained by the water. So you have here water being the one, 2 waters being the one gaining electrons to form hydrogen gas and 2H minus. So please understand that in the copper chloride solution, it is copper that is formed and the Cl2 that is formed. But in the electrolysis of sodium chloride, we are saying the chlorine is still formed. At the anode, we are fine. But at the cathode, it's not the sodium plus that gains electrons. Electrons are gained by 2 waters there, 2 H2O2 plus 2 electrons to form H2 plus 2OH minus. So I hope you have an understanding, or we have 2 molecules of water that gains 2 electrons to form H2 and 2OH, not sodium. So it's not sodium. It's only when we're using molten sodium, and our exam guideline talks to a sodium chloride solution, which means sodium chloride dissolved in water. So remember always that on this one is straightforward, we form copper and Cl2, but on the electrolysis of sodium chloride, we form Cl2 and H2 and 2OH, which means it's the water now that gains electrons. Now, the next process is the refining of copper, where we are purifying copper. And in this one, the emphasis that I want to make is that you will see that we're having copper that is impure at the anode side, and we're having copper that is pure on the cathode side. So we can have copper chloride or copper sulfate as our electrolyte there. Then we're able to purify. Hence, at the anode, we'll have loss of electrons at the anode. At the cathode, we'll have gaining of electrons. And then you will see that the anode will decrease in mass, the cathode will increase in mass. That's how we purify our copper. The last process is the electroplating process. That as well will be able to indicate, we'll have we're still talking electrolytic cell. We're saying we have a positive and a negative. Then we are having now the metal on the anode side. The anode side is the metal, and the object, it can be a ring, can be anything. The object will be at the cathode side, which is the negative one, and then you are able to have it plated like that. So those are the 4 processes that you must know. They are not difficult, and then we are hoping that you will, by end of this lesson, you will understand how we deal with these processes. Now we're no longer saying now this one because it's called electrolytic cell. Electrolytic cell is now referred to as the cell that converts electrical to chemical energy. So we no longer convert chemical to electrical like we do with galvanic. Now we're converting electrical energy to chemical energy. And this cell, we're saying, is non-spontaneous and endothermic. So energy is absorbed here. Energy is no longer released like it was released in the exothermic galvanic cell. Now, electrolysis is not a cell, it's a process. So the difference there, if we say electrolysis, you must say it's a process that converts electrical energy to chemical energy. And this electrolytic cell, we're saying it uses electrical current to force a particular chemical reaction to occur, which will otherwise not take place. That is very much important. It summarizes the whole section to say, as far as this cell is concerned, it's non-spontaneous because we're using electricity to force a reaction that was not supposed to happen. Remember, we said that the negative one, it will undergo oxidation, is your anode. The positive one, it will undergo reduction because it's your cathode. But in this one, we're going now to say differently, to say the positive now becomes anode and then the negative becomes cathode. Hence, the electricity is the one that is making them to become that which they become. Meaning now the positive is the one now that is going to lose electrons, the negative is the one at the negative electrode. That's when the gaining of electrons will take place. So I hope you understand that, or that's why we refer to it as non-spontaneous, because we are forcing a positive now to lose electrons, the negative to gain electrons. So we are saying then we can say that electrolytic cell is a device or an apparatus which is used for electrolysis, and we are saying when connected to direct current, one electrode becomes positively charged and the other becomes negatively charged. You see, it is the electricity that makes them to become like that. Without wasting time, we are saying here, don't panic. What does that mean? We are saying positive, the positive one. When you see positive, you know that is the anode. Remember, on galvanic cell, we're saying positive is cathode. Now we're changing. We're saying when it comes to electrolytic cell, don't panic. Positive is anode, negative is cathode. So the negative one now we're saying is a cathode. So you see the anode is positive and then cathode is negative. Hence we're saying don't panic. Don't forget, panic stands for positive anode, negative is cathode. So that will help you at all times. And we are having there our solutions. Remember, the cations will be attracted towards the negative electrode, which is cathode in this case. So it's still the same what we said, that you will have cations will go to the cathode and ions will go to the anode. It does not change whether you're doing galvanic cell or electrolytic cell. It is still like that. The flow of your charges, they will flow the same one. Now, you have to understand now that we are dealing here with solution which uses inactive electrodes. What does that mean? So we are saying, for example, when we are doing decomposition of copper chloride, we will use, for example, a carbon and a carbon inside a copper chloride solution there. So it's a carbon and carbon. Those two carbons are inactive, means that they are not taking part in the reaction. They just allow the flow of your current, your charges. Now they are able to remember. We said that carbon is a non-metal, but it's a good conductor of electricity. So it's just there to conduct your electricity, but they are not necessarily active electrodes. So there is no carbon that will decrease in mass in that sense, and then you are able to understand. So that happens during electrolytic cell. We have two inactive electrodes. In this case, can be carbon, or we can even use platinum. But now, in other processes like electroplating, you will be using one active electrode and one inactive, meaning that you'll have a metal that will lose electrons, and you on the inactive one where we have the object. For example, you want to make your key there, you want to make your ion key there to become copper. What do? The copper there the copper there, when the cell is in function, the copper will lose electrons. And when you go to the key there, what will happen? The reverse reaction will happen. The copper 2 plus will gain electrons to form copper, you see. Now, that is what we were talking about. So in this type of cell, you will see that the concentration, this electrolyte, the solution itself, does not change. It remains the same, because we are saying the rate of oxidation is equal to the rate of reduction. So it's important that you always remember that as we move with our reactions. Now, remember, we're still having two half cells taking place, hence we're just showing that they are in the same beaker, but they are still two, hence we're dividing them there to see that we still have anode side and the cathode side. And then they just that the two reactions are taking place in the same beaker, and we have a source, hence we're saying it's non-spontaneous reaction. And we always use a direct current source for polarity there, so that the polarity must not change. We cannot have positive electrode becoming negative, negative becomes positive after every cycle. Hence, we use a direct current source. So we've shown a battery, a source, a cell there that is showing that this is a non-spontaneous process. Now, electrolysis of copper chloride. We are saying copper is formed at the cathode and chlorine gas is formed at the anode. So I've already indicated that we are having copper chloride, and we are saying at the cathode, copper will be formed, at the anode, Cl2 will be formed. If the solution on which electrolysis is being performed contains a halogen, such as chlorine and bromine, the halogen will always form at the anode. Hence, we are saying chlorine will always be formed at the anode. That is for electrolysis of copper chloride as well as electrolysis of sodium chloride. Chlorine will always be formed at the anode. It's just that for copper chloride, we're saying copper will be formed at the cathode. For the sodium chloride one, we are saying chlorine will always be formed at the anode. So we know at the anode it will be chlorine. But at the cathode here for sodium chloride, it won't be sodium plus gaining electrons. It will be 2 water gaining electrons. I wanted to emphasize that so that we are able to move. Now, electrolysis. We are saying electrolysis of copper chloride. Further explanation. We're saying that the electricity is used to split this current to produce copper and copper. So we have copper chloride here that is split into copper 2 plus and 2Cl minus there. And then during electrolysis, copper loses electrons and then has an overall positive charge and becomes a cation, which is attracted to the cathode, or negative. So you're able to get that chlorine gains electrons, has an overall negative charge and becomes an anion, which is attracted to the anode. So you are able to see that now this is what is happening, and at the anode we are going to be able to have 2Cl minus becoming losing electrons to become Cl2 plus 2 electrons. So Cl2 at the anode. Remember, at the anode, we're saying there will be loss of electron, and we're saying positive is anode. At the positive electrode, where the anode is, there will be 2Cl minus losing electrons to form that. And at the cathode, we'll have copper 2 plus gaining electrons to form copper. So you're able to have that. And that is how our experiment looked like, and you are able to do that. So what I'm going to do now, I'm going to take you guys to the lab where we'll do this experiment, and you are able to see what we're talking about, because we don't want to just talk science, but now we want to see science. So let's go to the lab. We'll take a small break. When we come back, we'll be at the lab. We'll be doing this practically. Thank you very much. Welcome to this segment. Now we are going to focus on the experiment. We are going to do decomposition of copper chloride solution. Remember, when you say copper chloride solution, we are simply saying is copper chloride that has been dissolved in water. So there is water there, that hence we refer to it as aqueous solution, which means it has been dissolved in water. Now, for this experiment, we are going to decompose. Don't forget, we want to form copper and Cl2. That must be in your mind. To say when you decompose, we are saying in this experiment, we want to form copper and Cl2. Those are the two products that we want to get at the end of this experiment. The apparatus that we need two carbon rods, which we have here. I've already put this protecting box here to ensure that the two electrodes, they don't touch one another. So those are the two carbon rods. You can see them. And then we have the power supply. And then you will be able to see that for our power supply, I'm going to put it like that. I'm just putting it like this so that you are able to see the positive, which is red, and the negative, which is black there. And then we have our glass beaker. Now, our glass beaker will be using this glass beaker, which is a 250 mils glass beaker. However, there is solution already. I will explain. And then we are saying connecting wires. We're going to have our connecting wires, which is our positive, which is red, and our negative, which is black. So we've tried to use longer ones so that we're able to connect properly. So you will be able to see that as we run with our experiment. Now, steel wool. The steel wool is very much important, my learners, is to ensure that we clean these carbon rods before we start the experiment so that there is no contamination. So that is the steel wool of cleaning our electrodes. And then we're going to use 1 mole per cubic decimeter of copper 2 chloride. It's very much important to understand that this copper 2 chloride, you can get it as a solid. If you get it as a solid, you must first prepare 1 mole per cubic decimeter of that copper 2 chloride. In this case, I have already prepared for you 1 mole per cubic decimeter copper chloride. We're having 200 mils that we're going to utilize here. Now, these are our apparatus for our experiment. It's very much important that you remember when we start with this topic, we are saying panic, which means positive is anode, negative is cathode. So you're able to see this red one, that is our positive, and then the black one is our negative. So the negative, we are saying, is cathode, and then the positive is anode. Remember that at the anode, we said an ox. So at the anode, oxidation takes place, and at the cathode, we said red cat. And then we're saying reduction takes place at the cathode. So you got to understand all the time so that you are able to remember. This is our anode, which is said this anode is negative, and then cathode anode is positive, and negative is cathode. Now, with no any waste of time, we'll move to our experiment, which says pour the 1 mole per cubic decimeter chloride solution into the beaker. I've done that already. I've used 200 mils of 1 mole per cubic decimeter, and then clean the carbon rods using steel wool just to ensure that they are clean. I've cleaned them already, but I just wanted to demonstrate that you need to clean them so that there is no contamination. Now connect 1 carbon rod to the negative terminal of the power source and another carbon rod to the positive terminal of the power source. So you are able now to connect. It's very much important, and you must be careful always when you're working with chemicals. Hence, I've tried to wear some protective clothing here to ensure that I don't get any injuries and all that. And you are working with electricity as well. You will ensure that your wires, they don't touch. So you are having your positive and negative connected. Remember now, you are saying positive is anode. So when I connect this positive, I'm connecting it to the anode. That's how you will see the anode. The anode is positive. So I'm connecting the anode there, which is positive, and the negative is a cathode. So I'm connecting the negative, which is the cathode. So you see, everything was connected, and place the carbon rod in the copper 2 solution. This step that now we must put these carbon rods into the copper 2 chloride solution. So we do that, and then this next step, it says secure the electrodes firmly and ensure that they do not touch each other, which I already have done with this. And then now I'm able to correctly connect them. Immediately after connection, you are expecting some observation. I will try to put this so that you can be able to see clearly with no problem. I'm just trying to bring it closer to yourselves, and then you are able to check there. If you see something, you are asking yourself, and then I'm 100% sure that there are observations that you are making there, and your observation is that on this positive one, which we said is the anode, Positive, we said is anode. Negative, we said is cathode. So on the positive anode, you can see that there are bubbles that have been formed, and then that tells you that chlorine gas is formed. Remember, bubbles indicate a gas. So there's a gas that is being formed, and then we are saying that gas is chlorine. So you are able to see that at the anode, chlorine will be formed. And it goes to the theory that we have discussed earlier when we said as long as we have a halogen, it will form Cl2, and you will find the halogen always is at the anode. So we're saying at the anode, we're having a reaction where 2Cl minus is losing electrons to form Cl2 plus 2 electrons. And then we are now going to look at the cathode. What is the observation? Because you observe with your eyes, you're able to see. You see, what did you see? You saw the bubbles. What is the bubbles? What are they showing? They're showing that there's a gas that is formed. What is the gas that is formed? Is Cl2. Then it confirms that the reaction that is taking place at the anode is 2Cl minus forming Cl2 plus 2 electrons. Now, we move to the cathode now to be able to see. If you can look, you might not see, but immediately, if I want to now remove this, I must first unplug from the power source so that we don't have electricity here. Then we're able to look at what we're dealing with. So I'm having my positive, my negative, and then I'm able to remove them there. And then I have unplugged everything for you. Now we can go and do our observation. Look at this, beautiful. So you can see that in the negative one, which was our cathode, we're having the reddish brown color that has been formed, which means that copper was formed, which means we're having copper 2 plus 2 electrons forming copper. So remember, when we started the experiment, I indicated to you to say in this experiment, we want to form copper and Cl2. And indeed, Cl2 was formed at the anode as this reaction took place. And at the cathode, you were able to see that copper was formed. How do you know that copper was formed? There's a reddish brown color there. That reddish brown color is showing you that there is copper deposit on the carbon rods. So we were able to reach the aim of our experiment. Now, the other thing that I must not forget to let you know is that when you do like that, I can smell here, we're smelling chlorine because the chlorine gas is being formed. So it's very much important that as well you are using, you open your windows and all that, because you will have the gas that is being liberated there. So I hope you have seen this experiment and it will help you now to be able to answer the questions. Remember, we'll ask you questions based on the experiment. Don't forget, we had the positive, where we had our anode, where we said chlorine gas was formed. Then we had that connected to that one and the other one connected to that one. So you are able to draw now the cell diagram. It's a positive, which is that long line, and a negative, which is the small one. Remember, we said positive is the anode. So you are able to draw that we had a carbon and another carbon. And all these were put in one beaker, and then you are able to draw like that. And you are able to put copper chloride here. Remember, we said this copper chloride is aqueous, meaning that it's dissolved in water. And if you remember hydrolysis, we said it's the reaction between salt and water, and we said ions will be formed. So you are able to see that we're having copper 2 plus and 2 chlorine minus, and negative chlorine is attracted to the positive anode there. Hence, the chlorine now 2Cl minus is able to form Cl2 plus 2 electrons. And on this side, we have the copper 2 plus. Remember, the electrons are moving from the anode. Always electrons move from the anode to the cathode. So as the electrons move from the anode to the cathode, what happens is that copper 2 plus on the cathode will gain electrons and form copper. And indeed, we're able to show that because you saw that there was a reddish brown color that was formed. I hope this experiment will help you to always remember what happens at the anode, what happens at the cathode. But don't forget one thing. The main thing is that at the end of the day, during decomposition of copper chloride, we want to form copper and Cl2. And we're able to indicate that. I hope you enjoyed the experiment. And then thank you very much for this part of the experiment as we go back to our other lesson that we're doing. Thank you very much.
I want you to ask yourself these 3 questions. Number 1, what do I want? Do I want to become an A student, or do I want to become an average student? Number 2, I want you to ask yourself, how do you plan on getting there? Are you going to put more extra hours, or are you going to just sleep? Number 3, who will be with you in this journey? Because it is important that we associate ourselves with students who have the same vision as us, who want to become a student, who want to put in the extra work, who want to become better at what they do. Unsuccessful people do not plan, they just let life happen to them. But successful people are planning on how they want their lives to be. And right now, you plan on how you want your results at the end of the year to be like.
Welcome again. This time we'll be doing an experiment, our second experiment, which is electroplating. Remember, for electroplating, what we are saying? We're saying we're still using electrolytic cell, so it's still positive anode, negative is cathode. But what we are saying here, we're saying that now we have an active electrode, which in this case is copper. So we're going to use copper as our active electrode. Remember, the next thing that we need is the object, which is an inactive electrode. So our object can be a plastic, but if it's a plastic, you'll cover it with graphite so that it is able to conduct electricity. But for this experiment, we're going to use carbon. It's just indicating any object that you can get, because this is inactive. It's not taking part in the reaction, except that there will be plating on it of copper. Now, you might have to understand how this electroplating differs from the experiment we did earlier, which was electrolysis or decomposition of copper chloride solution. On that experiment, we had carbon and carbon, two inactive electrodes. But in this case, we're having copper that is active, meaning that copper is able to lose electrons and all that. But you are having carbon, which is inactive, which in that case is just like any object that you can just plate with copper. Remember, when it comes to the solution that we're talking about, we still have our power supply, our glass beaker, our connecting wires, our 1 mole per cubic decimeter copper chloride solution. And then we still have our steel wool that we use for cleaning the electrodes. But we have cleaned our electrodes as far as this experiment is concerned. So now I've shown you everything that we need. Now we're going to go straight into the experiment. The most important thing is that in this case, the copper 2 plus that will be gaining the electrons won't be coming from the solution, will be coming from this copper. So it is copper that is going to lose electrons to form copper 2 plus, and that copper 2 plus will gain electrons and be plated on this carbon rod. So you got to understand, hence we are saying the electrolyte, the solution here, will remain constant. The concentration of the electrolyte will remain constant, because it's only the copper 2 plus that is formed from this copper that is going to be plated on this one. Hence the solution, the concentration of the electrolyte will remain constant. But when you look at the experiment of decomposition of copper chloride, the concentration of the electrolyte decreases because we are busy forming the chlorine gas there. So you can see that the concentration, after some time, you will see color change there. But with this one, the color will remain the same. It will remain 1 mole per cubic decimeter, because the copper will lose electron to form copper 2 plus, and that will be plated on that one. So what am I saying? I'm saying at the anode, we are going to have a metal. So we have a metal at the anode, and at the cathode, we're having the object. Don't forget that. That's how you will know that that is one. So we are saying we have active electrode and an inactive electrode there. So now, if you look at the procedure, it's saying pour the 1 mole per cubic decimeter copper chloride. We're still using copper chloride solution there into the beaker. We have done that already. Clean both. I've cleaned both the rod, the carbon, and the copper. The copper and the carbon, they are all cleaned with the steel wool in this case. Ensure that the power source is switched off. It is off for now, our power source. Connect a copper rod to a positive terminal. So now, remember your positive and your negative. We've indicated that your positive is your anode. Your positive is your anode. You're expecting the loss of electron. We said an ox. At the anode, there is loss of electron. So we're able to connect now the positive to the anode like that, which is our copper rod. Now, the negative is a cathode. And the cathode is the one that we want to ensure that there is gaining. Remember, we said red cat, reduction takes place at the cathode. So you are able to connect. You can't connect it there. You must connect it at the top, because it must not be in touch with our solution. You are protecting it there with that box that ensure that they don't even touch. Now from there, we can be able now to place our electrodes inside our solution, and then we connected it nicely. Positive connected, negative connected. Now you remember what you want to see at the end of the day. You want to see electroplating. So you want to see that carbon rod must be having copper that has been plated on it. So now when it comes to observation here, you got to think about it. Remember, we're saying copper is going to lose electrons. So when copper loses electrons to become copper 2 plus, you are expecting that the mass of this copper will decrease. So the mass of the copper will decrease. Yeah. And we're saying the carbon rod is going to be plated with copper. So we're saying at the carbon rod, what is going to happen? We're going to have a reverse reaction of that, which is copper 2 plus 2 electrons forming copper. So you are able to see that the carbon now will increase in mass. The carbon will increase in mass. The copper will decrease in mass. Why? Because the one that is losing electrons at the anode now, it is the electrode that is losing electrons, hence it will decrease in size. So it will decrease in mass, and then the carbon will increase in mass. And we are saying the concentration of the electrolyte will remain the same. Why? Because the electrons that copper 2 plus is gaining are coming from the copper rod, not from the solution. Unlike during decomposition, because all the 2 electrodes are inactive. But in this case, one is active. The active one is the one that loses electrons. That is our metal. Our metal loses electrons. The object, which in this case we are using carbon, you can use any object, can be a ring, can be anything that you want to plate with, or maybe to make it more beautiful or to make it more shining. You can be able to put that object there, but it must be something that is able to conduct electricity. So we're expecting now that the mass of copper will decrease and the mass of carbon will increase, and we want to see the carbon now must be plated with the copper, because we are saying this is copper. We are plating the carbon with copper. Now, with no wasting of time, we're going to check our observation. I will first just disconnect to the power source so that we don't have any problem. Then I'm taking off the power source now. Now, remember, we want to see, yes, look at that. You can see that our copper, it has decreased in mass. When you look at it, our copper has decreased in mass, but look at the carbon. It's now plated with a lot of copper around it. That is copper plating. Sometimes you are finding somebody wearing something gold and all that. Electroplating is the process. We make stuff more shiny and we preserve stuff against rust and all that. So I hope now you have enjoyed and you have seen the experiment and you have made your observation that there is reddish brown pigment there on the carbon, which means that we're able to plate the carbon with copper, and then the copper was able to lose electrons to form copper 2 plus, and that copper 2 plus gained electrons and were plated there. The concentration of the solution remained the same. What is the reason? It's an exam question. We're saying the concentration of the electrolyte remains constant because the rate of oxidation is equal to the rate of reduction. So I hope you have enjoyed these experiments and they've made you even more interested in this topic. Thank you very much. Now we'll continue with questions and be able to answer questions based on what we just did. Thank you very much.
Believe in yourself. Believe a little more in yourself, because to those that believe, nothing is impossible. You have done this before. You have passed your tests before. You have went into a higher grade before. It is possible because you have done it before. Do not doubt yourself. Keep believing in yourself. Keep pushing, because this can be done and you can be great. You have been given power to decide whether you want good results in your life, in your schoolwork, or you want bad results. As Tony Robbins said, it is in the moment of your decision that your destiny is shaped. And your destiny is shaped right now with the decisions that you are currently making in your schoolwork. So decide whether you want to be an A student and start working on it, because there is power inside of you. The infinite power is inside of you, and the time you decide to tap in that power, you will become who you want to become in your schoolwork.
Thank you very much. We are back from the lab. Now we're back in class. Now we continue where we left, hoping that you have enjoyed the experiment and you have seen how the composition of copper chloride solution take place, as well as electroplating. Hoping that you will be able to do well in the exam and be able to answer questions. Now, with no wasting of time, I will move to the next part, which in this case is purification of copper. Remember, we said we do 4 processes. So we have done decomposition of copper chloride. The second process we said is electrolysis of concentrated sodium chloride solution. The third process we said is electroplating. And the fourth process is purification of copper. On this one, you will see that we are having copper that is impure and copper that is pure copper. And then the impure copper must be on the anode side. Remember, we're still using the same principle of don't panic. The positive is still anode. So on the anode side, we're having impure copper because we want electrons, this copper to lose electrons. Hence, at the anode and ox, we are always losing electrons. Hence, we'll lose electrons here. But the same thing that happened with electroplating, you will have seen we had a reaction that took place and then the reverse reaction taking place on the cathode side. So still here, we'll say the concentration of the electrolyte will still remain constant here. The concentration of the electrolyte is constant. So we're saying during purification of copper and during electroplating, the concentration of the electrolyte remain the same because the rate of oxidation is equal to the rate of reduction. However, during electrolysis of concentrated sodium chloride solution and decomposition of copper chloride, we're saying the concentration of the electrolyte decreases, meaning that overnight, when you've done the experiment, you're able to see that there will be color change. That color will now become colorless. And then when it comes to these ones, the solution, this color will remain the same as far as because it is the copper that is still losing electrons and the copper ions are being gained there. So we're saying the rate of oxidation is equal to the rate of reduction. Hence, we're saying the concentration of the electrolyte, even during purification of copper, will remain constant. Now, the other important thing, we're saying copper will lose electrons to form a copper 2+, and copper 2+ will gain electrons to form copper. Hence, we are saying on the anode side, the anode will decrease in mass, and on the cathode side, the cathode will increase in mass because now the purified copper is being plated there, and then we're having increase in mass in terms of that. So those are the reactions that does that. And then the other important thing that happens is that we have a mud there, anode mud, or you can call it a sludge that is formed. You can see when you are looking for copper, silver, gold, platinum, all those, they become part of the sludge which is formed. And you can see that that sludge has economic value because if you have gold, you have silver, you have platinum that is being formed during the purification. Remember, you're looking for copper, but there is something that is within the metal that is, we refer to it as an impurity, and then those, they form a sludge at the bottom. Just like when you're taking a bath, you're able to see the sludge that is formed there around. That is the same thing now. Our sludge here is made up of other metals that are there. So that is how we purify copper, and then which is the fourth electrolytic cell process that we do in grade 12. As I've emphasized that we do only 4 processes. Now, in conclusion, as we conclude our lesson, we would like to look at this activity, just straightforward activities, to say the diagram below represent a cell that may be used for refining copper, and then which one of the following half reactions will take place at electrode X. So you must be able to know that we say where we have the metal, that is the anode. Where we have the metal, that is the anode. And where we have the object, that is the cathode. So you're able to see that the impure, I want to put it this way, to say this one is refining of copper, then we are having impure. Impure must be anode, because we said we must break it down. Sorry for that. Impure must be anode, and the pure one must be cathode. So you know that this one, the impure one, the copper will lose electrons. That's what will happen. And on the pure one, we just write the reverse direction, which is copper 2 plus 2 electrons forming copper. So be careful not to confuse the processes, because when it's copper, purification of copper, you know that you must have the impure copper and the pure one, and then we're saying the impure one, you want to break it down, hence we're saying it forms the sludge. So you can see under the impure one, the sludge has been formed there. So you're able to see that. And the question was, which one of the following will take place at X, which you know that is the copper 2 that is gaining electrons to form copper, because that is the pure copper. So you have pure copper there, and then this one is losing, but this the copper 2 will gain electrons and do that. Hence we said the concentration of this electrolyte will remain the same. Now, activity 1.2 is saying the following characteristics may be used to describe electrochemical cell, electrolytic or galvanic. They are saying the one that is the chemical reaction is self-sustaining. The self-sustaining means is spontaneous. You know, galvanic is spontaneous, but electrolytic is non-spontaneous. Electrolytic is non-spontaneous. So you got to know that the other one, galvanic, spontaneous, electrolytic non-spontaneous, because we said energy is added. We use electrical energy, which is converted to chemical energy. The reaction requires energy from an electrical source, that is electrolytic. Only this one applies to electrolytic. This one applies to galvanic. Now the anode is the positive electrode of the cell. So you are having the anode as the positive electrode of the cell. Remember we said panic, positive is anode, negative is cathode. So this helps you to remember that, okay, this must be electrolytic. So now when you go to the question, it's saying which of these characteristics are specific to an electrolytic cell. So already you have seen that electrolytic cell is not self-sustaining. So number one, Roman figure 1 is wrong. The reaction requires energy from electrical source, correct. We said we use the direct current source. The anode is positive anode, negative is cathode, correct. So you know that Roman figure 2 and 3 applies to electrolytic cell. Hence, you are able to push and choose D and get your 2 marks there. So I hope that helps you even as you prepare to answer as many questions as possible. Copper is purified through electrolysis as represented the simplified diagram. I didn't show the diagram. Which one of the following statements is correct for purification of copper? You know that for purification of copper, we're at the positive, negative is cathode. So you know that negative is cathode and positive is anode. And you know that the main thing that you must understand is that at the cathode, the copper 2 gains electrons and forms copper. At the anode, the copper loses electron to form copper. So you are able now to see that, okay, at the anode, there must be loss of electron, not gaining. You look at this statement, it says copper 2 are reduced. It means copper 2 gains electrons at the positive electrode, which is anode. We don't gain electrons at the anode. The last statement says copper 2 ions are reduced at the negative electrode, which is the cathode. You know, at the cathode, copper 2 gains electrons to form copper. So this will be a correct answer, which is your number D. So it's very much important that you go through all the statements and you are able to choose the correct answer with no problem. Which one of the following is formed at the cathode during electrolysis of concentrated sodium chloride? This one is very much important because I've indicated that when we are having sodium chloride, we are at the anode, we are going to form chlorine gas. We agreed on that one. But we said sodium does not gain the electrons. The electrons are gained by water. So it will be 2 waters plus 2 water molecules plus 2 electrons forming hydrogen gas plus 2 OH minus. So you're able to form that. So what are we saying? We're saying, oh, what is formed at the question is, which one of the following is formed at the cathode? So at the anode, chlorine gas is formed. We talked about that. But at the cathode, we said sodium is not the one, sodium ions is not the one that is formed. So it's not chlorine that is formed. It's not sodium chloride, it's not oxygen, but it's the hydrogen gas that is formed. So you are able to answer that question and get your 2 marks. So I'm hoping that you will go and do many questions, but I would like to end with the statements. And I'm saying to you, practice, practice, practice. Practice as many question papers. Answer them. The more you are doing questions, the more you understand much better. He said, Albert Einstein, anyone who has never made a mistake has never tried anything new. So continue to try, continue to do things that looks difficult to you, because sometimes things are difficult when you start, but when you go on, you are able to realize that sky is the limit and you are able to get them correct. I'm wishing you all the best. Thank you for watching this lesson. See you next time. Goodbye.